Yeah, okay. So this is our next question. Okay. So we need to optimize this. So let's just dive right into it. Our function has three variables now, as you can see, x1, x2, and x3. So let f of x1, x2, x3 be whatever this is. Okay. Like you just need to write that stuff again. So I decided to skip it. It's the same thing only. Just copy this and write it here. Then we have our constraint. Okay. So our constraint h1 is equal to x1 plus x2 plus x3 equal to 20. But we shift the 20 to the other side, so it becomes minus 20. And now we define our Lagrangian function. So our Lagrangian function will have x1, x2, x3 along with one Lagrangian multiplier for a constraint. So we get Lagrangian function as f of x1, f of x2, f of x3 minus lambda 1 h1, which gives us basically this. Now we just copy paste this and this are the same thing only. So just jotting that down. Thanks, so. Now, since we jotted that down, what else do we need? Yeah, this is basically a function, no? This is a Lagrangian function, whatever the stuff was. x1, x2, x3, and lambda 1. A bit crumpled, but finally. Okay, so now we just need to calculate the partial derivatives with respect to x1, x2, x3, and lambda 1. So we calculate the partial derivative. Here you could write defining Lagrangian function. So we get 4x1 plus, oh, okay, we calculate this and put it equal to 0. Calculate it with respect to x2, the derivative, and put it equal to 0. Calculate the partial derivative of the Lagrangian function with respect to x3, put it equal to 0. And same with respect to a Lagrangian multiplier and put it equal to 0. So the first one we get as 4x1 plus 10 minus lambda 1 equal to 0. First one. Then our second one is with respect to x2. No? So 2x2 plus 8 minus lambda 1 equal to 0. And a third one is 6x3 plus 6 minus lambda 1 equal to 0. And our last equation that we would be obtaining is x1 plus x2 plus x3 minus 20 equal to 0. Now I'll just enter these equations into the calculator. We get 4, we have only x1 here, so x1 ka coefficient, then x2, x3 have 0, and then lambda 1 has a coefficient of minus 1. The 10 we shift to the right side, so we get a minus 10. Then for the next one, we have no x1, so 0 x1, 2 is the coefficient for x2, no x3, so 0, and lastly we have a lambda 1 of minus 1. And this 8 can be shifted to the other side, becoming a minus 8. Then over here we have x1, x2 as 0 and x3 as 6. So x1 0, x2 0, x3 as 6, and our lambda 1 has a coefficient of minus 1 as always. The 6 when shifted to the other side will give us a minus 6. Lastly, for the last one, we'll have 1, 1, 1, no lambda over here, and we'll have 20. This is the only one with a positive coefficient. When 20 goes to the minus 20 goes to the other side, it becomes positive. And now we just solve. So we get x1 as 5, x2 as 11, and then x3 as 4, and lambda 1 as 30. Yeah, so this has 30, and then yeah, then we basically got a stationary point. No, our stationary point is 5, 11, 4. Nice. Now we need to determine whether this point is a point of minima or a point of maximum. So for that, here we have three variables and one constraint. So 3 plus 1, 4. So we will be calculating the del 4 matrix. Also, along with this, we also need to check del 3. That's just the condition, okay? So now for del 4, we basically have 0, del h1 by del x1, del h1 by del x2, del h1 by del x1. Oh, wait, there will be another column here with respect to x3 as well. Del x2, h1 by del x3. Now a differentiation of a Lagrangian function. The diagonal elements are the easiest. Is basically the same variable square, double derivative. Then this will be with respect to x2, then x1, differentiate partially with respect to x3, then x1, and these ones are like the mirror images. So del square, this is x1 x2, so this will be x2 x1. This is x1 x3, so this will be del square x3 x1. This one would be del square del x3 by del x2, and this one would be the reverse of that, del x3 del x2. Nice. This is a del 4 matrix. From this very matrix you can get your del 3 also. If you look at this part here, this much, this is basically this part over here is your del 3, and the entire matrix is your del 4. Okay, so you do not need to calculate the partial derivatives repeatedly. You could just use this del 4 matrix for your calculation, so you could simply get your answer. Now for del 4, as you can see, our constraint h1 is this. No, so del h1 by del x1 will give us 1, del h1 by del x2 gives us 1. Similarly, del h1 by del x3 also gives us 1. Let's fill that up first. 0, 1, 1, 1, and same entries are there vertically, 1, 1, 1. Correct? Now let's calculate these entries. For that, we can look at these. Okay. For double derivative with respect to x1, we get it as 4. Double derivative with respect to x2, x1 square, x2 square is equal to 2. The double derivative of the Lagrangian function with respect to x3 is equal to 6. And all other derivatives, if you notice, like del square first x1 then x2, or del square first x1 then x3, all the rest would be 0, 0. That is because these first derivatives only have the same variable in them. They do not have any other variable in them. So that's just a quick trick, okay? So if you ever notice something like this, then you can directly write those as 0. So we have 4, 2, 6. Those are diagonal elements, 4, 2, and 6, and rest all are 0. And for del 3, you don't need to, you could just write this much part of the matrix, okay? This part of the matrix. And then after writing that formula, you can just copy paste the values from here, like these values. So you get 0, 1, 1, 1, 4, 0, 1, 0, 2. That's your del 3 right there. Now I'll just quickly calculate the values of del 4 and del 3 and be right back. Del 4 is a 4 cross 4 matrix. Yep, see, this is del 4 entered. Now entering del 3. This is our del 3 entered. Now going to matrix calculation, finding determinant of our first matrix. We get the determinant of del 4 as minus 44, and we can also find the determinant of del 3, which is minus 6. Since del 3 and del 4 both are negative, we can conclude that this point is a point of minima. That is our point 3, 5, 11, no? 5, 11, 14, our stationary point that we just calculated. 5, 11, and 4. This one. This is a point of minima. Now, in order to find the minimum value of the function, you could just substitute the values of phi means x1, x2, and x3 in the. So I'll just do that now. We get the value as 281. Therefore, this is our function. On substituting, we get 281, and this is the minimum value of our function.